In the previous video, we saw the matrices On, which are the n by n matrices, such that A transpose equals A inverse. These are sitting inside the invertible matrices called GLN, and traditionally we talk about orthogonal matrices over the real numbers. Now, it turns out that many of our formulas are much more sensible and much more convenient to work over the complex numbers. And many engineering problems, the complex numbers are a lot more effective than the real numbers at solving the problem. So we want to extend the idea of orthogonal matrices in a useful way to the complex numbers. So what is the analog of On over the complex numbers? Now, of course, the orthogonal matrices came from the notion of the dot product. So ultimately the question is, what is the analog of the dot product over the complex numbers? And the answer is actually quite simple. The motivating principle is that we want it to look like the dot product, but we need to be sure that it always returns real numbers, because if we want to measure the length of a vector, that length should be a real number. We're not really sure how to interpret a length like 3i plus 5. So here's our definition. This is called the Hermitian inner product. Often we write this with angle brackets, VW, but ultimately the important part is the definition. That definition is written one of several ways. Either we write V star W, invoking the transpose notation from orthogonal matrices, or we write this as, more precisely, V bar transpose W, where V is the complex conjugate, and star simply means transpose bar. Or, more succinctly, one could write V bar dot W, where dot is the traditional dot product that we used before. We'll stick with the V star W notation because it's most convenient and most brief. To see why our formula for the Hermitian inner product, V star W, is so useful, let's go back and think about complex numbers. If I have a complex number Z, for example, 3 plus 4i, I want a reasonable notion of the length of that complex number. Now, if we think about the complex numbers as lying on a plane, x, y, and z is x plus iy, then the length of a complex number should be the corresponding hypotenuse of the triangle connecting the origin to x plus iy. In this case, we have 3 and 4, and of course, this is a 3, 4, 5 triangle. 9 plus 16 is 25, so the hypotenuse is 25. Now, how do we compute that in a sort of abstract way? Well, if I look at the quantity z bar z, that would give me 3 minus 4i times 3 plus 4i. Remember that the complex conjugate is taking the imaginary part and flipping its sign. It's reflecting across the real axis. This quantity is now 3 times 3 is 9, and with the plus and the minus, the cross terms cancel. And the last part is minus 4i quantity squared, but of course I squared is minus 1. So this is 9 plus 16 is 25. So z bar z is our expression for the length squared, the modulus squared, of a complex number. Now, when it comes to vectors, this is exactly what we need. For example, suppose that I want to compute the Hermitian inner product of V and W. So I'm going to compute V star W, where V is 3 plus 4i, and 0 plus 6i, and W is 1 plus 2i, and 5 plus 5i. So first of all, I can simply compute this. V conjugate transpose W is what I get by computing the product like this. Notice the signs have flipped in my imaginary parts because of the conjugate, and of course the transpose has put this in row and column form. So here we have 3 minus 4i times 1 plus 2i plus 0 minus 6i times 5 plus 5i. 3 minus 4i plus 6i. Now, minus 4 times 2 is minus 8, but with the I squared, it's plus 8. And then we have zeros and minus 30i and plus 30. Again, minus, but the I squared makes it a plus. So overall, we have, let's see, 38 plus 3 is 41, and negative 30 plus 2 is minus 28. So assuming my arithmetic is correct, which you probably ought to check, V star W, the Hermitian inner product of these two vectors, is 41 minus 28i, a complex number. So that seems sort of mysterious, but it's less mysterious when we consider what it does for magnitude, or length. So for example, let's look at V star V, which is 3 plus 4i, 0 plus 6i. That was my V. So V star V does exactly what we want. So I have my row vector and my column vector, but I have flipped the signs here because of the star, the conjugation. And now if I take 3 minus 4i times 3 plus 4i, we already know that that is 9 plus 16 is 25. And minus 6i times plus 6i, the minus cancels with the I squared to give me plus 36. Notice that this is a non-negative real number. Moreover, what it is it's the length of 3 plus 4i as a complex number squared plus the length of 0 plus 6i as a complex number squared. In other words, this is what we should reasonably call the length of V squared. It can only be 0 if each of these terms is 0, meaning that each of the complex numbers was 0 to begin with. So V star V is the length of V squared, just as over the real numbers, V dot V is the length of V squared. So now we have one more step to do. Consider a matrix A from Cn to Cn, which is non-singular. We could ask, what is the condition that AV star AW equals V star W for all V and W in Cn? In other words, what's the condition that this isomorphism of Cn preserves the Hermitian inner product and therefore preserves length? By the way, it also preserves angle, but our notion of angle has to expand to be a complex angle, which is more like an exponential or a logarithm than it is like a traditional sine or cosine. Okay. Following the same procedure we did for the orthogonal matrices, you can see almost immediately that this version using the transpose conjugate still holds. And by choosing the appropriate basis vector, we conclude that A star A is the identity. The same argument as before using the standard basis. Therefore, A star is equal to A inverse. Such an A is called a unitary matrix. And these matrices are called UN, sitting inside GLN over the complex numbers. One final remark is that UN equals ON over the real numbers. And that's because A star is a transpose conjugate by definition. And if A is real, so all of its entries are real numbers, the conjugate has no effect. So the formulas are the same in that case. So the unitary matrices form a perfectly reasonable extension of the orthogonal matrices to the complex numbers in such a way that they respect the notion of length that we want for our vectors of complex numbers, and that if we happen to be looking at real numbers, it reproduces all of the features we see in the orthogonal matrices that we're used to. The unitary matrices are going to have a profound effect on the geometry of transformations, and therefore on the geometry of the data analysis that we want to perform. Okay, that's where we'll stop for now with unitary matrices, and we'll pick up with some applications next time.